is Luis David Alvarez Corrales, and I'm doing a PhD at Telecom Tech. I'm going to talk about cooperative clusters in cellular networks, specifically about the nearest neighbor model, a joint work with Anastasios Giovannidis. So this talk is about modeling the irregularity of base station locations in cellular networks by point process. Which in the Poisson case, the main advantage is to give explicit formulas to measure the performance of the network. Specifically, I'm going to talk about cooperation. Why cooperation? Because it increases coverage and provides better service to cell edge users, as it has been shown in Bachelet Giovannidis' work, or Nigan Minero Hengi, or Akum Heath work. For example, this is an example of a dynamic cluster where every user, the black dot, is served by its 4 closest base stations, the blue dots. For example, this one is going to be served by these 4 base stations because they are their 4 closest base stations. And these 2 users, they're going to be served by these 4 base stations and these 4 base stations, this one. The problem here is that this base station must cooperate with these 3 base stations and with these 3 other base stations. And this generates a problem because it cannot do it at the same time, so we'll have a problem of time sharing. And we want to avoid this kind of stuff. So we propose static groups. Why static groups? Because cooperation driven by the user, as in the previous example, may overburden the backhaul control channel. And fixed cluster minimize information exchange and infrastructure between base stations cooperating with each other. And there's no need to consider time sharing between base stations, as I said. This is a first example of an static clustering. Clusters are formed by those base stations, the blue dots, inside each square. For example, these 4 base stations is a cluster. These 2 base stations is another cluster. The problem with this clustering is that it's not optimal in the way that, for example, let's suppose that this user lies here. So let's suppose that it's going to be served by this cluster. In this case, the signal is going to be weaker than the interference generated by these 2 base stations. Or, for example, if we suppose, okay, he's going to be served by its closest base station and its cluster. In this case, let's say this one. So it's going to be served by these 2 base stations, but this base station is going to generate a strong interference also. So we want to avoid this kind of stuff. And a more pragmatic approach is to define a priori static groups by means of proximity. Why proximity? Because we want a strong signal and weak interference. We propose the nearest neighbor graph. This is a cluster formed by the nearest neighbor graph with maximum group size equal to 4. These 4 base stations, they're going to cooperate. These 4, they're going to cooperate. This one is not going to cooperate with any base station because this base station is its nearest neighbor, but this base station it cooperates with these 3, and there are 4 elements. So this cluster has size equal to 4, so it stops here. So this is going to work. This base station is going to work by itself. Okay, so. What about our model? What would we like? Given a topology for the locations of the base stations, like this, our first goal is to define a clustering procedure like this. That means that we would like to partitionate our base stations in cooperative clusters. And for a given user, the stations of each cluster either give service or they create interference. We consider the approach where the typical user is located at the origin, that is stationarity of the base stations. We suppose that 1 user is served per cluster. And if we note like this, the cooperative cluster serving the typical user, the signal received by the typical user is this function of the cooperative cluster serving the typical user. And the interference received by the typical user is the sum of all the interference generated by the cooperative clusters, but the cooperative cluster serving the typical user, where the functions if and g model the interaction between the elements of each cooperation group. In this work, we bound the maximum group size by 2, so we only have pairs of base station cooperating or singles. Why? Well, we bounded because we don't want a big number of base stations serving only one user, and we bounded by 2 because for some mathematical problems. And well, the cooperation group definition is based in the nearest neighbor relation. Specifically, fix a realization of base stations. The base station X has as its nearest neighbor the base station Y, and we noted by this if Y is the nearest base station of X. A pair of base stations are in mutually nearest neighbor relation if one is the nearest neighbor of the other one and vice versa. A base station is called single, and we noted by this if it's not in mutually nearest neighbor relation with any other atom of phi. How can we see that? Let's suppose that we have these 3 base stations. So, because X is the nearest neighbor of this is the second one. Okay, so X is the closest base station to Y, and Y is the second is the nearest base stations of X. They're going to cooperate. But in the case of W, X is the nearest base station to W, but W is not the nearest neighbor station of W because it's Y. So he's going to remain single. He's going to work by itself. So fix a realization phi. We define the point measures phi1 and phi2 just like this. Phi1 are all the single points of phi, and phi2 are those points that cooperate. And given a stationary process phi, capital Phi, we define the point process phi1 and phi2 by means of the dependent thinning defined above. So phi1 is just all the realization of phi1 of the single points of phi, and for phi2 the same. This is in the Poisson case. We have this realization where the connected points represent the pairs and the single points, for example this one, all the single base stations. So this is just an image. We have a first theorem for a Poisson process with density lambda. Given 2 base stations, the probability of these 2 base stations cooperating is given by this expression. Moreover, there exists a number independent of the density of the process and of X, such that the probability of a base station cooperating is P star, and the probability of X being single it's 1 minus P star. This is easy to see because the first expression, it's only the empty space probability of the Poisson process, where the surface, which it has to be empty, is the union of these 2 disks. So it's easy. And this number is just the integral of this expression all over the Euclidean plane. A little bit intuitive. So first conclusions, we have that approximately 62% of points are in mutually nearest neighbor relation, and around 38% are singles in the Poisson case, obviously. It's impossible for phi2 to be a Poisson process because, by definition, all his points are in mutually nearest neighbor relation, not like this, so he's not. However, for phi1, we had to use numerical and statistical tools to verify that it's not a Poisson process. A numerical result for the Voronoi cells we have that the average surface of single cells is larger than the average surface of atoms belonging to pairs. So as a first assertion, we have that there's an attraction between pairs, which is obvious, and we see a repulsion between singles. So this is we were concerned after this about these properties of repulsion and attraction of our new point process. That's why we need to use these functions. The nearest neighbor function is denoted by capital G, is the distribution function of the distance from a typical point of the process to its closest atom. The empty space function, denoted by capital F, is the distribution function of the distance from a typical point of the process. And the J function, given by this expression, is a function measuring repulsion and or attraction between atoms. If it's bigger than 1, it's an indicator of repulsion. If it's smaller than 1, it indicates attraction. I remark this because the nearest neighbor function is the distance from a typical atom of the process. The distribution function of that. So we needed to find an expression to the pound measures of our new processes. So in the Poisson case, we found it. If we note by Px, P1x, and P2x the pound measures of the original process, phi, phi1, and phi2, respectively, we have that for every event. The pound probabilities are given by these conditional probabilities, which are well defined because these two events they have a positive probability because of the first theorem. Why? Because Ax, it's only the trajectorial property of being single, and Bx of the trajectorial property of being in a pair under the pound measures of the Poisson. So it's really intuitive. We can give an heuristic proof here, but we don't have time, so we're going to skip it. And thanks to this, we have this theorem where we found the nearest neighbor function of phi2. We found an analytical representation, which is good. Unfortunately, we couldn't do the same for phi1. So, but here we have some numerical results, which are the blue line. This is the nearest neighbor function of phi1. The nearest neighbor function of phi2 this is this one in blue. And this red one, it's only a comparison between an independent thinning of a Poisson process with the same rate as this one. So we see that they're far away from each other, so we cannot use the nearest neighbor function of an independent thinning instead of the function we want. With the empty space function for both, we didn't find any expression. These are numerical results, but we see that in the case of phi1, in the dependent thinning and the independent thinning, they really look alike. So we could use it. And these are the J functions. In the case of phi1, it exhibits repulsion, and in the case of phi2, it exhibits attraction because here is bigger than 1, and over there it's smaller than 1 everywhere. Well, to finish, we will talk about interference, in this case generated by phi1 and phi2. The interference generated by phi1 is only the sum of the interference of each single point, and of phi2 is the sum of the interference generated by all the pairs divided by 2 because we're taking twice each cluster. If Vx represents the random propagation effects from X to the typical user, some examples of the interference generated by each cluster or each single, it's, for example, this one, so the interference generated by the single is going to be the sum of orthogonal signals. And for the pair, we can have orthogonal signals or not orthogonal signals, or here, for example, we take the maximum of the orthogonal signals generated by each base station, or we only take one by an independent choice by a Bernoulli experiment. These are some examples. We have this first theorem. We find the first moment for the interference field for both of the interference field. But this for general if or general G, so we can use whatever we want here. We have some simulations and also analytical. The lines there are the simulation, and the dots they are the analytical evaluation, so they fit. This is for when we have a path loose exponent to 0.5. This is the interference, generated outside a ball of radius r for the singles, and this for the doubles, for the pairs. So we can see that our numerical results and the analytical evaluation, they fit. And well, we have this. We found the intensity measure as a corollary, so we can conclude that over any finite surface of the Euclidean space, the average proportion of single points, it is 1 minus p star, and the average proportion of pairs, it's p star. Well, to try to find an expression for the Laplace transform of both processes, we had to use a finite window approximation for any surface on the Euclidean space. We define phi 1a as the points of phi inside A, which are single with respect to the points of phi inside A, and phi 2a are the points of phi inside A in mutual nearest neighbor relation with another point of phi inside A. And we will approximate the Laplace transform of phi I by the Laplace transform of phi A. How does it work? Well, for example, this is a realization of the process phi 1a and phi 2a, where A is an open ball with center at the origin. So this is phi I. For example, this belongs to phi 2a because they're in mutual nearest neighbor relation, and this is a single point inside A. The problem is, if we see outside this ball, we have other points, which is the complete realization. In this case, this point, it's single, so it belongs to phi 1a. But for the whole process, it will be in pair because these 2 points are in mutually nearest neighbor relation. Or in this case, these points belong to phi 2a, but we can see that these points, they work in couple, not with this one. So those are the edge effects we can see, and we have to deal with it. However, if we define these functions and we fixed a finite number of points, of deterministic points, H, A, I, N is just an indicator an indicator of xi being single. So that's it with respect to these points. And for the Laplace transform, we give an ugly expression, but it's pretty intuitive. Let's focus only on this. Here we can see that we're using the uniform distribution of the points of the Poisson process, which is independent also. And if we note by f the vector of the interference generated by these points, we only care about the interference generated by those single points inside A. So this is intuitive, but it's not numerically tractable. Well, for phi 2, we do the same. This is an indicator of xa working in pair with some other point here. And we have a similar representation for the Laplace transform. And here we can see the uniform distribution of all points. And we only care about those points working on pairs, where G is the function given all the possible combinations of interference generated by these points. Well, conclusions. For every stationary point process, we construct cooperation clusters via the nearest neighbor relation. In the Poisson case, the two resulting point processes are they are not Poisson. However, we found some properties of these two point processes: the average proportion of singles and pairs over any surface, expressions for the palm measures which are numerically tractable. So it's good. The nearest neighbor function of cooperating atoms, first moment of interference field for single and pairs, and expression of the Laplace transform. If you want to see all the results and proofs and everything, they are here and in this paper, and it will be presented in SPASWIN 2015 in Mumbai. Future work, we would like to find some bounds for the nearest neighbor function of phi1, the empty space functions of for both process phi1 and phi2. Higher moments for phi1 and phi2, primarily the variance. We only have the expected value. Use the above results to analyze performance of cooperating cellular networks with measures which are functions of the CNR. For example, the coverage probability, the throughput, or the delay. That's what we would like to do. And thanks for your attention. If you have any doubt, you can write to me or ask me or whatever.
So, any question? It's very interesting the process phi1 that you generated that exhibits repulsion between points. It's well known that it's very interesting to find point processes like that, and that determinantal processes are very difficult to generate in practice. So do you know if there is any convergence result or any approximation result between this kind of process and
via Poisson, or
they are not Poisson?
Yeah, they're not Poisson, but approximation.
So if so here you have phi1 and phi2. If you increase if you have phi1 and phi2 and phi3, you make a clustering. Does this approach to a complete repulsion like a determinantal process? Do you have any intuition about this?
Not yet. We focused only in these two thinnings, but I guess you were talking about a third one, which would be process of cluster of size 3.
So you have a kind of point processes that exhibit repulsion between points that is called the determinantal
okay.
process. So my question is there any result that or any intuition to approximate this kind of determinantal process by this thinning process of Poisson?
No.
No, it's not the same process. Because the reason is that you have a result that is independent of density. And determinant point processes are very dependent on what density have the atoms. So depending on whether you want to have a big repulsion or a lower repulsion, the result this will result in a different density of your process. Whereas here, the interesting result is that we have a result totally independent of the density. That means that always for any density we have like 63% of points that are in pair, and 37% singles.
Yes, but it's for phi1. It's for
phi1,
and it's only for 2. If you want to play with this, you can increase to 3 or 4.
Yeah, but the independence result will remain. Whereas in the determinantal processes, as you can define how much attraction or repulsion you can have, but this will give a different density to your system. So it's very different processes. We had also some questions on that, but I don't know if there is any relation.
Sorry.
Just a general question. So you are starting with the Poisson process. Do you think that Poisson process is well adapted to the real world with base stations?
Well, no, but it gives us formulas. So
Actually, I have a similar question actually. I mean, you assume that all the base stations are uniform. They have similar characteristics.
yeah, there is that. Yeah.
Yeah, okay. And this grouping, clustering, you do it just by taking into account the geometrical distance between the, not the attenuation, not the channel property.
No, but it doesn't
Yeah.
make any sense to take so.
No, I mean, what makes sense for transmission, for the use of bandwidth and transmit power, that has to take into account the channel properties.
True, but not, we consider fixed clusters. So the clusters are predefined, so the idea is that
No,
you put
so
a cable
I'm
and connect the
So
stations.
I'm coming to a similar question as Ludovic. So if the base stations are having same properties, same transmit power, and they are operating in similar channels, why won't you spread them equally and forget about all this clustering?
Well, actually,
I mean,
here I did it. Well, we did it, but we used a stationary process because if our process is stationary, the nearest neighbor is unique, so it's well defined. But in the Poisson case, you can use it a non-stationary process, and you can define stuff like this because the density, it will only have to be how is it called? It will have to be an integral of the Lebesgue, a function of the absolutely continuous with respect to the Lebesgue measure. So like this, we can have results, not all of them, because we need, in this case, we use theorems like the pan probability of the Poisson process is to your trajectories, you only add the point x. So, well, here you can use it everywhere, but we use also other theorems about the stationary Poisson process. But you can define for in the Poisson case for not a stationary process, and you can have also result, not all of them, but you can, yeah, it's not only for stationary process.
no, it's very different from. Okay, so let's go back, go to another point. Can you show those interference curves?
Which ones?
There was only one set of results with the red and, yeah, this one. So what is it exactly?
Okay. This is interference generated outside a ball of radius r.
Interference for whom?
What?
This is interference experienced by a user who is at a station.
By a typical user, yeah.
At a certain point from a base station?
Yeah, from the origin. So this is the interference received by the typical user, generated by the single points.
Yeah. It is interference or signal to interference?
Interference.
Okay. And 0.5 is close to the base station?
Yeah. When it's close to the base station, the interference it's infinite.
No, I mean.
This is the distance from the typical user to. Okay, so if we.
So the typical user has a serving base station and everybody else.
We don't consider serving base station.
So this is the signal, the level of signal
Exactly. Received by the
yeah.
user.
So this looks yeah.
Okay.
Yeah. That's okay. So this you call it interference, but I mean the amount of power the user will receive from that base station. It's just the D2 alpha term. And when you have 2, then it is 3 dB above. That's it.
Okay. Sorry.
Yeah.
Last question?
I've got a question.
from my point of view, your process can be seen as a stable matching, where your acceptance list is reduced to 1, the closest neighbor. Have you investigated what the process will become if, for instance, you allow a size of the acceptance list of 2? That means that if you can't negotiate with your nearest, you try the second next, and otherwise you give up.
No, I didn't understand.
With that, you will be able to adjust, I think, the proportion of single and pairs.
By choosing some other user other than the closest.
Yeah. When you have full acceptance list, for instance,
I know the matching algorithm, yes. Then you could essentially arrive to 100%, like, because...
Yeah, but you have a continuum with just 2.
But why should you do that? Because, why should you do that? Because...
For instance, when you got 4 pairs very close one to the other, you may, in the end, have just 1 pair and 2 singles, but maybe it would be better to have 2 pairs.
2 pairs, yes. But maybe not, because if it is in between, maybe this will
yeah. Just saying that you can do that to adjust the proportion between pairs.
These are things that we have just started working on, so we don't really know what would be a good result for the I think it's a very open subject, and there are many things to discuss about, but I think that putting clusters in the network is something that has already very nice properties, and there are many things to investigate. But, you know, I mean, other ideas are always
Welcome.
until proven.
Yeah.
Okay, let's thank you again.